All right. Where it gets a little bit more interesting maybe is how much should I invest for 6 years at 3% interest to earn 400 bucks. So I want to earn $400 in interest. I need to know how much money to put into that account if it's simple interest. So that's a more of a solve equations type thing. We're looking for how much our principal investment should be on an account for 6 years that draws 3% simple interest. And that's an easy, algebra 1 kind of solve equation. The 0.18 p divided by 0.18. $400 divided by 0.18. We need to put $2,222.22 into an account so that we can earn 400 bucks in 6 years. Simple interest is not the way the bank does it. So you're not going to use that at your local bank in a savings account. They don't do it that way. They do compound interest, which is what we're about to do. I'll give you a chance to copy all that down. All right. Compound interest. A little bit more involved formula. So that formula is A equals P parentheses 1 plus R divided by N, close the parentheses. That entire parenthesis is raised to the N times T exponent. So this is an exponential model here with the compound interest formula. Right. Now, over here on the right, you get what everything equals. R is the rate, just like it was in the simple interest formula. It's going to be a percentage. We need to convert it to a decimal. N is going to be how often the interest compounds. So they do different accounts do different amounts or compound differently. My regular savings account at the bank compounds quarterly, which means how many times a year? 4 times. You have accounts that compound annually, which is 1 time a year, semi-annually, 2 times a year. You have some that compound monthly, 12 times a year. It depends on the situation, and the problem will tell you how many times, what it's doing. If it says quarterly, that's 4 times, semi-annually, 2 times, that sort of thing. It's going to tell you that. T is going to be in years again. Again, with finances, T is in years. P is the principal investment. It's how much is in the account to start with. This one, A, is your account worth. It doesn't just figure the interest. It figures what the account is totaling at the end of that's where the 1 plus is in there. That's going to get you the principal plus whatever you're earning in interest. Okay. So let's apply this a little bit to see there. We're investing 1,500 bucks at 2.5% interest, compounded quarterly for 4 years. So this is almost the same problem as example A was, but instead of simple interest, we're doing compounded quarterly for 4 years. So we want to know what's the account worth after that. So $1,500, 1 plus the rate, 0.25. Quarterly is how many times? 4 times. And then 4 times 4 as the exponent. And we can just crank that out with the calculator. Honestly, that's what you're going to do. You don't even have to simplify it at all. Just type it straight in. 1 plus 0.025 divided by 4. Close the parentheses, raised. I always just multiply that exponent out. 4 times 4 is 16. But you could type it in 4 times 4 there, and it would still work. Crank that out. $1,657.24. 4 is one. The first 4 is quarterly. The second 4 is 4 years in the problem. So it's how many times it compounds each year times how many years is where that's coming from. So 16, 57, 24 cents. Yes. Yeah. Monthly would be 12 times 4. That's the idea. Okay. All right. Let's get into a little bit more college algebra speed with this particular problem. It says, how much should I invest in an account worth $6,000 after 6 years? So I want it to end up being $6,000 after 6 years at 3.25% interest compounded monthly. Okay, so I'm taking this formula and I'm saying, okay, A is $6,000. I don't know how much I'm investing, but I do know I've got an account that I can put some money into that draws 3.25%. So 0.0325, and it's compounding monthly. So it puts the interest back in every month, and then monthly. And I'm going to leave whatever I put in there. I need this $6,000 to be there at the end of 6 years. Maybe I'm running a business and I know I'm going to need $6,000 to replace at the end of 6 years. I'm going to replace some sort of piece of machinery in my business, like a copy machine, or maybe I've got some sort of investment. I need to have $6,000 laying there in the time. So I'm going to save that money through this account that I've got set up. So we want to solve this for P. What's all of this over here? This right here. It's just a number. It's all numbers. There's no variables in that part. The P is the variable. So we just got this big number here times P. So to solve this, divide by, that 6,000 by whatever that number is. That's an ugly decimal number, but we just divide 6,000 by it. That's what tells us how much to put in the original account. All right. And to the 48, or no, not 48, 12 times 6 would be 72. 72 exponents. Dividing both sides by that, whatever that number is, it's like 1 point something. You can do it. You're going to have to get that number eventually anyway. If you wanted to, in your calculator, figure out what 1 plus, 0.0325 divided by 12 raised to the 72 power is, just don't round it until the very end.
Yeah, I didn't know the calculator would round it.
It's gonna, if you use it like this, it's gonna store all. It only shows you 10 places there, but it stores more than that, so it doesn't round it. Okay, so you can get it with the calculator and use that. It's rounded afterwards. Okay, so we're going to take 6,000 divided by that number. So I just press the up arrow and grab that number. So $4,938.31 is what I'm gonna want to put into that. $4,938.31. If I've got that much capital in my business right now, that means I can put that money away, and at the end of the 6 years, when whatever I bought, is gone, I need to replace it. I'm gonna have $6,000 sitting there ready to replace that. Not exactly the American way. We want to just borrow it and go on, but it's a good idea. All right, let's look at another one similar to that, but we're looking for a different variable here. So we want to know how long do we need to leave our $1,500 bucks. Let's say we're graduating this spring, and we've gotten, we sent out a bunch of invitations to people we hadn't seen in years, and they all sent us a check for $100 back, or $20 or whatever, and it totaled up to be $1,500. And then I had some that I was going to use on my senior trip, and then so I'm going to put $1,500 into a savings account, and I want to know how long am I going to have to leave that there if that savings account draws 1.5% quarterly, if I want it to be worth $2,500 at the end. So how long am I leaving it there? So on our formula, A equals P 1 plus R over N to the NT. What are we looking for if we're looking for how long? We're going to try to solve for T, which is the exponent. So we're going to use logs and things to help us solve this. Okay. So we want the account to be worth how much? 2,500. So that's the A. We're putting how much in there to begin with? 1,500. So that's our principal. 1 plus 0.015. Quarterly is how many times a year? 4. Our exponent here is 4t. We don't know what t is. So we want to solve this for t. So multiplication going on here, so I'm going to undo that by division. It'll be 5 over 3. Now, the variable is in the exponent. How do I get it out of that? How do I bring it down to the front? Natural log, yeah, because the bases are definitely not the same here. 5/3 and then whatever that length is. Definitely not the same. So I could take the natural log of each side. Natural log of 5/3 equals 4t natural log 1 plus 0.15 over 4. Now, what do I do to get t by itself? By what? And the rest of that natural log stuff. And this is going to be approximation in years. So on my calculator, I'm going to ln of 5/3, close those parentheses, divided by, and to divide by all of that stuff, I'm going to use a set of parentheses in the denominator and just type it all in at once. 4 times the natural log 1 plus 0.015 divided by 4. Close the parentheses twice. 34.11 years. Or 34, we'll round to 2 decimal places, so that'd be 0.12. That you're going to do approximation every time on these with the finances. No, to keep it going there. So there's some examples of compounded interest when it's compounded different amounts each year. It doesn't matter which one. If you use log base 10, it would get you the same decimal equivalent there. We just a common log. We use natural log because this textbook tends to use natural log more than does anything else. So that's why I used it. All right, the other type of interest that we could have would be continuous interest. And continuous interest is like every second of every day, it's dumping the interest back into the account. So it's like if they kept increasing in the original, in the compound interest formula, if n kept getting bigger, it would get closer and closer to e to the RT is what happens. So we get this A equals PERT is the way I remember that. I don't know if y'all know what PERT was a shampoo. I don't know if they still make it or not. But anyway, that's the way I remember that. A equals PERT. And P times E to the RT is what that is. The P is the principal investment. This E is that number E that we've been dealing with some in this chapter. R is still the rate. T is still time in years. As we're dealing with that. Little different interest problem here. It asks us when we want to double our investment, which is always a good thing to double your investment, at 5% continuous interest, continuously. So to double an investment, what's it doing? It's multiplying itself by 2, right? What's the easiest investment to double? $1. I'm going to invest $1 and double it. So that this is equal to 2 equals 1 e to the, we know the rate. $1, double it. If they ask me to triple it, I'm going to triple $1. They ask me to quadruple it, I'm going to 4 times $1. That's the easiest thing to do there. They ask you to multiply an investment by a certain amount. Pretend that investment is $1 and then work it out. It's going to work out the same whether it's $1 or whether it's $1,000 to double it. Okay. All right. Doesn't seem like it would, but it does. So we did divide by 1 here, and that gets us 2 equals E to 0.05t. And then what do we do to get the exponent down? Natural log on this one is going to do a little something different. Yeah, that cancels out the E, so it's a little easier problem. We get 0.05t is equal to the natural log of 2. So we would just divide by 0.05 and get our time. How much? 13.86. Yeah, 13.86 years. Take us 13 years to double an investment, no matter what the investment was. $1 to $2 or $1,000 to $2,000. Or for us teachers, like $1 million to $2 million, So. All right, there's a couple of quick formulas here for the rest of the section. Effective rate of interest. What the effective rate of interest formulas are, it's still the R and the N's are all the same thing. R sub E is effective rate of interest. That's what it means. What it does is it takes compound interest, and if you apply this formula to the R and the N, it'll convert that interest rate to what it would be if it was simple interest. So it's a good way to compare two investments. Like if they say compare this investment, at 6% interest for compounded quarterly to an investment that's continuous interest, but it's only 5.5%. You could get the effective rate of interest and compare those two, and that would tell you which one's the better investment. The better simple interest rate is the better investment. So those formulas are just plug in, work out, and get the number, compare the numbers. The bigger the number, the better.
What was the E called?
The E is just the exponential number. It's the effect. This is R sub E is effective rate of interest. That's what that's not. This E is effective. This E is the E number. So it's a little confusing, but it's the same notation as we're using there. Okay. All right. So there's 6.7. Let's go to 6.8. The point of that is to compare different accounts. Like if they ask you which one is the better option, I'll put the problem back up here just a second. If you're going to compare two investments, one that maybe was at continuous interest and one that's compounded quarterly, it's hard to compare those two based on that because there's two different formulas for those. But if you do the effective rate of interest, what that does is it gets them to what if they were simple interest. This is how you can compare it. You compare those effective rates of interest, and that would tell you which one's a better investment. So it's used to compare accounts is what's going on there.
We're putting these together.
Yeah, putting these together. Exponential growth and decay. We're also going to talk about Newton's law of cooling and heating goes together. And then logistic growth and decay. We'll do just a quick thing with that. But exponential growth and decay, that's something you've seen before. Newton's law, you may not have done before. I don't know. It depends on, I don't know if they do that. Y'all do that in chemistry or not. You may have. I remember doing it in chemistry when I was here, but that was, 16 years ago, 17 years ago, 20 years ago. So, I'm getting old. So here's our formulas. There's two different formulas here. They're the same. There's no difference in them. It's just what letter they pick. And this one uses an A, like A sub 0, e to the kt. This one uses an N sub 0, e to the kt. They're the same doggone equation. There's nothing different about them other than one's an A and one's an N. It doesn't matter. So just memorize one of those. Know one of those. And it's going to work for law of uninhibited growth of cells. One of them's supposed to be for life science, and one's for another application of it. They're the same problem. Okay. Exponential growth and decay is the same whether you're talking about carbon atoms or you're talking about bacteria. It works the same way. Okay. All right. So K greater than 0. If the rate there is, if it's greater than 0, if that K is bigger number, talking about growth. If that K is a negative number, talk about decay. That's how you're going to recognize that. It's really easy to recognize based on what that exponent is. If that exponent's positive, then we're talking about growth. If that exponent's negative, we're talking about decay. That makes sense, right? T here, since we're talking about growth and decay, T can change. In finances, T always was in what? Years. In bacteria growth, carbon dating, T can change as far as that. And they will tell you in the problem what your time signature is, whether it's in days or hours and things depending on that. Okay, so these formulas are exactly the same. Nothing ever changes about those. Okay, so let's look at maybe they give us this equation, and they say this comes from some bacteria growth or cell growth of some sort. Doesn't matter what kind it is. It could be the strep strain, or it could be a flu virus that they're growing in a petri dish. It could be something. Doesn't really matter what it is. But there's some things we can answer based on that equation, and we're going to answer those questions. Number one is, what's the initial amount of cells?
100.
Why? That's right, but why? It's the A sub 0. What that stands for is the initial amount. It's 100. Also, if you ever forget that, when something starts, what's time? What's the amount of time? 0. If you plug a 0 into that, you get e to the 0 power is 1. 1 times 100 is 100. So it's really finding the t of 0 being that. But 100 is correct. That number that's right there should be your initial amount. 100, and we'll do grams. I didn't tell you that it's in grams. Science, everything's measured in the metric system, so we'll do grams. 100 grams. What's the growth rate? So the K is 0.045, which converted to a percentage would be 4.5%. Okay. Usually growth rates or decay rates are in percentages. So you just convert that decimal, that's the K, over to a percentage. Move the decimal place twice. The graph of that, could we graph that with the calculator? Probably, yeah, I know we can. So let's graph it. 100 E. To get the E, hit second natural log, 0.045, and then instead of T, we're going to use X, because that's what our calculator likes. And then we're going to have to hit zoom. And then here's the great thing. Zoom fit is what I'm looking for. Just 0. Zoom 0. And you'll get the picture. Isn't that nice? Is that growth or decay? Growth. Could we have told that without the graph? Yeah. You guys, a positive growth rate, right? A positive percentage on the growth. On the K value, it was positive. So we should have known it was growth anyway. But it's an increasing graph. That's something we need to keep in mind. So that's an increasing graph. I'm gonna make note of that it's increasing, which equates to growth. All right, let's get to a problem that's actually, we got to do something. What is the population after 5 days? So that tells us right there, T is in days, is what that tells us. T is in days for this particular problem. So N of 5 equals 100 E to the 0.045 times 5. You're just cranking out the number there. So 100 E to the 0.045 times 5. Round it to, let's go 2 decimal places, 125.23 grams. So real easy, just cranking it out. Number 5 is a little bit more college algebra level. How long will it take to reach 140 grams of bacteria? So, right. So you got to figure it's more than 5. But how are you going to figure out exactly how long? Plug it in where? For what? For the N of T, yeah. So this side over here, we're going to set it equal to 140. And we're going to solve for T. So this is like the continuous interest problem. It's exact same formula, really, except for instead of going from so it's like going from $100 to $140 with continuous interest, but it's growth. So I divide by 100 and then do natural log. That's right. Good. So it'd be 7 over 5. And then, like I said, do natural log of both sides. Natural log of 7/5 equals 0.045 T. Divide by that. And get that decimal out of that. 7.48, almost 7.5 days to increase from an initial amount of 100 grams to 140 grams of whatever we grow in there. If it asks us to triple the population, what would we set it equal to? 300, because we have an initial amount there. If we don't have an initial amount, we'd say the initial amount's 1, triple it's 3. We have the initial amount being 100, so we'd set it equal to 300. They asked me to double it, I set it equal to 200, that sort of thing. Really, really easy idea there. Let's see. Let's get a Newton's law of cooling. So we're not even going to solve that. We know how to solve that. You guys have gotten really good at that. Let's scoot on down here to the Newton's law of cooling. Because that the next example was the exact same thing again. Newton's law of cooling. I'm going to give you this formula for sure. I'm not going to ask you to memorize Newton's law of cooling formula. There's a lot of working parts to that. Okay. U of T of lowercase t. Capital T in this problem is your room temperature. Lowercase t is time. U sub 0 is your object's original temperature. So like if you had Newton's law of cooling is used like if you're trying to predict time of death for a body that's found. They use core temperature and measure what the temperature in the room was, and then they know how fast a human body cools off. Kind of morbid thought, but that's one of the applications of this. So all of these are numbers here that you'll have, and then the K and the T, e to the KT, that's the exponential part. The K being that cooling factor for whatever object you have. For a human body, that K is a special number. It's a certain number for a human body. It's a special number for a piece of iron. It's a special number for a bottle of Yoo-hoo. The Newton's law of cooling and heating it works symbiotic. It goes back and forth there. So it's the same. It's a different number there for every individual object. T again is time, and usually it's in minutes because cooling is much faster than anything else. All right, so let's look at this problem. An object is heated at 100 degrees and is then allowed to cool in a room where the air temperature is 30 degrees Celsius. So as long as your temperatures are in the same vein, so you can't do Fahrenheit and Celsius, you would have to convert if you needed to. Most of the time they're going to give you both of them. Okay.
May I have your attention, please? I have a list of people that need to report to guidance. Emily Mack, Megan Crow, Chase Burdett, Nolan Bryant, Logan Alfano Webb, Brittany Jaggers, Vanessa Johnson, Brianna Curtis, Dustin Parrish,
We'll finish this up on Monday.
Dakota Parrish, Mercedes Jackson.
Just get this written down. We'll finish it up on Monday.
That is to guidance at this time.
I thought we took a little longer on the quiz than I thought we should. Well, I probably should have. We'll finish this up on Monday.
I'm going.
Okay, yeah. You might want to take your stuff. The bell's about to ring.
To report to the front office, right here, got it. Logan Raines, Jonathan Ross, Vanessa Vaughn, Kyle Sims, Tristan Scott, Kayla Moore, Gary Cook, David Hazel, Austin Mayfield, Todd Pulley, Caitlin Reed, Abel Wolf. And then I need these people to the office: Carly Henry, Chris Austin, Andrew Atkinson, Grant Young, and Hunter Butler. Thank you.
All right, we'll finish this up on Monday, and then